Okay, I think we're recording. Might as well go ahead and get started. So this is the August 2022 community meeting for Pravega. It's been, I guess, a while since we've had one of these. I just want to overview some recent community developments that we've had going on. Raul attended in person KubeCon EU 2022 in Valencia, Spain, where we were able to have our first booth. So we'll be doing that again. At KubeCon North America, I'll review that here in a little bit. Also at KubeCon EU, we presented a virtual project office hours, a couple of presentations that are up on YouTube. Autoscale end-to-end in the cloud from storage to computing. That was by Brian Joe. That talk, he shows scaling Flink workers based on Pravega segments. And he demonstrates how that keeps stream processing up with real time. So it's a more efficient way of processing real-time data. And then another talk we gave at KubeCon EU was real-time quality control system in manufacturing. That's a streaming video and computer vision AI demonstration with Pravega used as edge devices. And then recently, Raul presented to the first workshop on serverless computing experience and exchange on elastic data streams in Pravega for serverless computing, and how Pravega is a good match for the serverless paradigm. And then the 0.12 release cycle will be starting soon, or 0.12 development should be wrapping up for release soon. Also, the Pravega steering committee was expanded with Brian Joe. He's been very active in the Pravega ecosystem team, and especially the Flink and Spark connectors. He also made the first open proposal to improve the Pravega release process. So the first proposal to sort of modify Pravega's governance came from him. And Raul Gracia has been very important to Pravega Core and has made some significant contributions to Bookkeeper and open messaging benchmark. So he's done important work on, I guess, correctness and performance of Pravega. And then upcoming, we've got KubeCon and Cloud Native Con North America 2022. That's in Detroit, Michigan. It's October 26th through 28th. Pravega will be staffing an in-person kiosk at the Project Pavilion, like we did for KubeCon EU. So if you can attend KubeCon North America, we'll be happy to see you there. And recently published a blog post about change data capture with Pravega and Debezium. It overviews the Pravega sink that's inside of Debezium and how to sort of set that up and get a development environment going. And then on today's call, Olivier Nougier is our feature presentation. He's going to demonstrate his ZIO connector. It's here at github.com/cheleb/zio-pravega. It's ZIO's kind of a type-safe, composable, async, and concurrent stream processing framework. And then after his presentation, I'll quickly overview recent features of Pravega in 0.10, 0.11, and then ongoing work. So I'll go ahead and stop sharing and turn it over to you, Olivier.
Okay, thank you. Okay. So, hello everybody. So I'm Olivier. I'm working at Ledger, in a crypto company in Montpellier, France. So we talk about ZIO and Pravega. So as Derek said, ZIO it's not a real framework; it's rather a toolkit to build a massively concurrent application in Scala. So I will start with some basic Scala stuff to the minimum Scala toolkit to understand the following. So ZIO, of course, functional. What are functional effects? Which is the core of ZIO, and of course the component, the some small coding session and demo. So the very basic difference between Java and Scala, it's more syntax stuff. You all know what is the interface in Java with I don't know not the square bracket, the superior and inferior sign.
Ankle bracket, yeah.
Equal bracket, sorry. And in Scala we have square bracket, okay, to define generic parameters, and more or less the return value are in the other side of the line, okay, at the end of the line, and nothing more. Also, when we have a small basic class in Java, the Pojo, I said plain file with final fields. This is a supplier. I think it's a function that takes no things and returns something. In Scala, this is clearly more short as definition, but they are the same definition. Okay, we have a run, which is a function, which takes nothing and return. Okay, I think it was the same signature in Java. I don't practice Java since for 8 years, so sorry for my approximation. So what is an IO? An IO, it's an effect. So it's a class, the case class, Pojo, okay, with only one field, which is a function that produces something, A in this case. Very simple example. I have an IO that produces a long, which is just when it will be invoked, will give the current time with milliseconds. So it's a value. It does nothing, and to obtain the result, you have to call more or less the method it contains. So in Scala, there is no static elements. There is only singleton. When you want to add static method, you just have to declare a singleton. That's how it's done. It's the same file, same name object in the same unit of compilation, same file, and you can add method that will be static, more or less. This method allows cleaner syntax to build IO. Not this part, which is A colon and an arrow. That means that this element won't be evaluated at this point. It's a kind of lazy, it's wrapped into another function. And then I can build another IO like this, just calling succeed, and there is no more the empty parentheses and the arrow, which was not very convenient. Okay, so there are only values. Okay, blueprint. It's just nothing. It's not like a future. Okay, it don't run. It must be evaluated later. So imagine we have this IO of A. So it says that it will produce A at some time. We add a method, a map, to transform this IO of A to an IO of B. Okay, IO A to an IO of B just by applying a function A to B and wrapping in the another IO. It's a row. We could do this in Java, I guess. It's nothing very complicated. For example, I have a tick, so my method that produces the timestamp, and I can map to with a function that transform this timestamp to string. I have an IO string. Then I can also map to a function that print. The print doesn't produce anything, so it's an IO of unit. In the same way, there is a possibility of composing IO between together. From an IO of A, I produce an IO of B at the end, but this time I apply a function from A to IO of B. This is really the functional effects way to do this. It can be strange, but it's not very hard to understand. In fact, we see there that the run are called twice. Okay, it's just the two IO that are combined together to build another IO. So combining two effects together. Very simple example. Let's imagine we want to define a method that take an arbitrary IO, so an arbitrary IO, and measure the time it took to execute. So from an IO of, I don't know, it's an IO of whatever you want, a string, of, I don't care. It will return an IO with a tuple, the time to execute, and the result of the IO. It will be done like this. I have this IO. I take the time. So the tick gives me the time when I start. I execute my IO. I execute the tick again. I take the end time, the start time, and I produce and I expose the value. The value. It's NT because end is a keyword in Scala 3. So I produce like this an IO from another IO by combining 3 times everything. It works. It's not very easy to read. Okay, so that's why in Scala we have a very fancy construction. It's called for comprehension, which is kind of we reverse the arrow. You can see this is the IO there that are producing the things, and in the end I produce I yield the result I want. Okay, this is exactly the same code, more or less. It's just syntactic sugar we are very abusing in Scala. So it's important to understand this succession of plot map and a map is there. Plot map, plot map, plot map, and a map. Also, to make a main in Scala, it's like Java, but of course in Scala we want things shorter, so we can do this like this. And everything, the whole body of the object is the main function. So now I have an IO. I build an IO like this. This is the IO this time. So this thing is a value. So if I run this program, you won't do anything because the value is just if you have a string somewhere, if you don't print the string, you won't do anything. So to execute this object, you have to give it to runtime. This is what is working under hood, but of course it's simpler. You just have to use another kind of main, and this is you just have to implement this method, give the IO you want to run, and that's it. Everything is just value, and value have this nice property to be interchangeable. Okay, we can remove them, the same result. It's what people call, I don't remember, the referential transparency, something like that. And it's very easy to reason about because you know that a value you can move it. There is no side effects, so very easy to refactor your code, for example. So this was a kind of IO, not the IO. The IO is quite more complicated in the sense that it's not just producing a value. It's from an environment, I can either produce an error or a result. Again, this is not how the IO is very implemented, just a high-level vision. So to resume, because I want to show code as quickly as possible. The IO are value, which are describing effects. It's not running. It's not like a feature. Feature, when you run the feature, it's started. The IO is nothing, just a description. I can produce this with this kind of error and something like that. It's very composable via flat map, which are done with for comprehension. It must be run, of course. There is an induction mechanism. I will demonstrate with some code. Many combinators, error channel, and it's run on kind of light thread. Some people call this a green thread, I think, in some other time. And we call this fibers in Scala, coroutine in Scala, in Kotlin, I guess. It's not a native thread, it's an applicative thread, much tighter and cancelable, many nice features. Also very important, there is a way to compose I/O from I/O level, to abstract some constructor. It's called the module pattern. It's kind of, I think, complicated to understand when you are not used with I/O and Scala, but it's important because it's allow us to scale our program very smoothly. So let's imagine we have a class like this, which is a kind of a repository to access a database. From an ID, I can retrieve a user. And what we have to read there, it's this is a function that take an ID, so an ID is the value, and return another value. This value is a zio, RIO, because it cannot fail. No, it's failed. Let's say it's an IO. And what this syntax says, is that I need a user repository, and given a user repository, I can transform an ID to a user. This is a fake implementation, of course. And now, sorry. This is the singleton object tied to the object, where I expose kind of abstraction of a constructor of this service. It's called a Z layer. The layer is nothing than an IO wrapped in an abstraction of this constructor. And this in this singleton object, I repeat this function. It could be a name with another name, but for simplicity, it's the same name. And then I will be able to call user repository, find this ID, and it will extract the service from some kind of injection engine, which is the environment, and run the method. I will give us an example quickly because it's so I jump to my code. There, it's no, so you can see this is just a Pojo, okay, a user. I am my repository, and when I want to run the application, now I can call this method on the singleton. This method, as you can see, produces IO that depend on user repository to produce a user. So, in fact, if I remove it, I will have a compilation error. Well, not this one because it's too big. Sorry. I just want to remove it. Let's see. Well, again, it's a compilation time, of course. And he said, "Oh, you want to run this this effect, but this effect depends on a repository. And to provide this repository, there is an API where I can give the layer. The layer is just the abstraction around the constructor. Of course, if I run this, it runs smoothly, and I can say hello to the rack. Nothing very fancy. What is interesting is that you see there the program is just zio that depend on the zio that depend on a repository that made fail with a throwable and produces nothing. I made other repository to illustrate how it can be used. Imagine I have also some addressing with address report, find by ID. I can take the ID, the address of the user, like this. Now I have an effect that depends on a user repository and an address repository. Okay, just at compilation time, you can the compiler is used to infer the dependencies of the effect, which is quite funny. Here I have to provide my layer. It's not exactly the same function. For macro details, not important. And now I can run this, and using the result, which is address. And as you can see, it's very easy to combine different services without Spring or whatever injection mechanism. It's just the compiler that is used to do this. In a more perhaps, I don't know, funny way or usable way, let's imagine I have a service that depends on my two other repositories. It's quite common. This time I can build a layer from from a function that will the compiler infer everything. Okay, because this is the class with the type dependent, and of course this value are inferred by the compiler. And now if I want to use this service, it's nothing more than this. I will ignore the result. It's postal service, send email to this time again, I have a program that depends now on user repository, address repository, and postal services, only by using the compiler. And of course, as you guess, I don't just have to add the layer that produces this. And everybody is happy. I can run my program with nothing very interesting. What is very well done in zio is that there is this magical macro that build everything and also provide debugging information. Sorry, like this. And you see in the log, you can see that the layer needed to execute my IO, my effect, are built, were provided, and this one was initiated from the other. Always at compile time. So there's nothing at real time, which is a kind of mojo in Scala. This. That's how we can build services and wire them together. Also, which is very important, is add some guarantees about resources. File must be closed, connection must be closed, connection to stream manager, for example, in Pravega, must be closed cleanly. This is what the zio are called resources. And this is very funny how it is managed. I will show you quickly. Imagine this repository now is an autoclosable. So of course I need to implement the method. I will just say print closing. Sorry. It's 2S. And this time it says that I want this method to be called at some time. It won't be called without some operation. The operation is very easy. It's just that this layer that was producing the repository, I say now this repository, I want you to register a finalizer to this IO, and it's just like this with finalizer auto, because I have an autoclosable, so it's very easy. Then now, if you look at the program, we see that we depend. It's not shown by the compiler. I don't know why. Sorry, I need to provide something that will be able to garbage I would say the connection. And now if I run the program, I see that at the end of the IO, I called the closing feature. I will use this to close cleanly the connection to Pravega in the following section. So to recap, zio are just value. They are highly composable, resource safe, okay, with a scope effect which are scoped, and when they exit the scope, some finalizer are executed in right order, and dependency can be delayed with a z-layer. So we are jumping now to Pravega, zio. I have three parts: an admin to create the resources, stream, table, user groups, stream part, and table KVP table access. Oops. So we are jumping now to the code. I have a Pravega running in the background, of course. And let's see how we can create have access to Pravega cluster and create some resources. So if you are used with the Pravega API, you know this is not this is a pure Pravega API. The stream configuration, because I will create a stream there and the scope before that. So we will see the pattern I show you last time. This is a singleton object. I have a method. This method will retrieve the Pravega service from the injection mechanism from the environment. Follow the create scope. It's an interface because I try to do this not too dirty. You can see the implementation, and the implementation you will see is very straightforward. Create scope, like to see. Here I have another IO that will retrieve the stream manager, which is again pure Pravega API. And you see, this is something that is blocking because there is some network stuff. So doing this, the IO will run the IO in the blocking thread, and I attach a finalizer to this IO because I want the stream manager to be closed when the process is ended. And it's everything it will be like this. Now I have a stream manager. I can check if the scope already exists. If it exists, I will return false because I don't create the resource. If it don't exist, I create the Pravega API to create the scope and return the result. That was this. Okay. Now here we have a boolean through is a resource is created. Same thing for the stream. So we can run this because my cluster is empty. Just run the scope, just created the scope and just created a stream called UTF-8 stream. That was how to use the administration. And we have, again, this program is an effect, that depend on Pravega admin service and scope to manage the finalizer. They are provided at some time before being executed. Now I have a same kind of structure to write to the stream. Again, this is a Pravega API to obtain the client config from a configuration file. There's some facilities, but okay, it's not very important. Some greater settings where I put the serializer for you. This is just a simple method that will make a test stream of 10 strings, and so I build a sink, same pattern, the singleton that extract the component from the environment, follow the call, just interface. And what is a sink in zio-pravega? It's just, in fact, you should recognize the Java API. I just create an event writer. I attach in a finalizer to ensure that the cleanup will be effective. This is a writer that is wrapped in an IO that will be finalized. So I don't even if it's failing, it will be mostly. I just try to see if there is a key extractor. If there is a key extractor, I just write. If there is no key, I write without key. And if there is a key, I extract the key and write the event with the key and the event. And this is lambda, okay, from the event to a task that return nothing because it's a feature. I just push this lambda to this sink and wrap unwrap the scope to ensure that when the stream will finish, every scope will be clean and the writer will be closed. That's it for the write. And so now I can have a sink. I have this sink with there. I just take my stream, make some debug here to have something moving on the screen, and run the sink. I can run to the sink. So if I run this very easily, just write everything to the Pravega, and now I can read in the same way. It's always the same pattern. Okay, I have a singleton. I will create a reader group, another singleton to create a stream to read the stream source, kind of a stream source to read from the stream. And I can now use my stream, tap to see the result. I take only 10 elements because it will not end if I am not limiting this. I take the count and print everything to the screen. This. Up, I read my all events. Of course, in different orders because you know if you notice there is 8 partitions, and so the order is not guaranteed, of course. And that's it. So, here I have my program that depends on Pravega in service because I create the reader group in the same IO, the scope to clean to finalize the resources, and the Pravega stream service. Everything is provided there. It's quite repetitive, as you can see. Sometimes you can see it's quite boring, but it works quite well. So it was the admin and the stream. Pravega recently added exposes some KVP table. So in the same kind of organization. So I have there some resources to create this KVP table. As you can see, I have a string because I will make another stream, which we call person stream. With so I have a stream to write some person that will be serialized, and the table called edges in the same scope. So I create everything with this. I will create and run this. I can run this. I added a person stream, a table edges, and a edge a table where I with some things. So this time I want to write to the stream. Then I want to read from the stream concurrently and write to the table. Okay, and read the count of edges. It's a quite stupid example, but the idea is that my test was a test. This is a test stream. As you can see, I will read some person, and their edges will be modulo 10. Okay, so the edges will be from 0 to 9. And the idea is that I will concurrently write 10% and using a more writing with two threads, two fibers in the table to ensure that the write are correct. So let me see concurrent write. I don't know if I have time to go into details.
Yeah, plenty of time, sure.
Yeah, okay. So the first I made some yesterday. It's write to table. Okay. So on the first example, I just want to write to table. So I will there build 100% in this sink, push this in the stream person stream. You see there is some fancy operator. Some people like them. And so this is the part just to fixture the test. Then I want to write to the table. So here I have a sink to write to a KVP table with some settings, and this is the function that how do you say this? That update the value. Okay, this is just an addition. Sorry, just with that. What do you say? It says that sorry, not this should be read like this: the old value, the new value, and what is the result? The result is O plus N. So plus N. Okay, it's the same thing. Scala like some we are used with this kind of syntax. So this thing will take an int. Okay, I'm not sure I'm very clear in that with the explanation. I have a key KVP table with int to int. The idea is that I want to count people per edge. So the key is the edge and the value is the count. So the idea is that I want to take my stream of person. I take 100%, build a tuple from the edge to the count, to the value, and run this to the table. So if I run this one time, I will have, of course, 10% because it's 10%. It's just a modulo on 100%. So it's attended. But I had only one stream there, okay, to read. And what is funny is that now if I want to write concurrently, what I have to do is this. I have another IO. There, the same thing to write to the table, and this time I will make two streams. In fact, I've extracted the method. Okay, to build the stream there, take only 50 person and push them to the sink, and I there one sink and one stream writing to the sink and another sink writing to the sink. This call is forked, meaning that they use fiber dedicated to this stream there, and then I join this fiber to ensure that the two streams are finished before exiting the IO. So now I can run this. You won't see any differences, of course, because it's working. I hope. So I have a nice counter. And if you want to see what's happened, in fact, I guess you know the API. Sorry, I have to see this in debug. As we see that there is some conflict. Sorry, I was. Where is my? If I run again with the debug information, of course it's quite noisy. But if I look this, I see that sometimes I have this error, which is expected, because I have two fibers that are writing to the same keys in different order. So sometimes there is a conflict. Okay, and you will see how it's implemented to retry the writing to the table. I find this very elegant. I hope you appreciate it too. So how is built the sync? That's the question. Always the same pattern. Okay. You see, when I say it was boring, I have a singleton method. This boilerplate. This should not exist, in fact. But because of recent evolution in Scala, there is no more support for annotation macro. So before that, there was macro to remove this, like Lombok, but we have to wait some Scala evolution to be able to see that again. This is a sync, and I find this very funny, personally. Not this one; it's a table sync. Sorry, I wanted the table sync. So table sync. When I say it's every time the same pattern, it's very boring. Okay, sorry for the indentation. So I have a sync there. And for the implementation, this is the table here. Okay, here's my sync. It's some code factorization, but the important part is this observed function that receives the key, the value, the table where I want to write, some settings to that, and the combine function. Okay, and what's happened here? I have first IO that attempt to retrieve the value from this key. Of course, there's two cases. Whether it's null, there's no value. So I put an insert command. I build an insert command, or there is already a value. And then I put an update with the combine function, providing the value of the previous version. Then here I have the table entry update command from zio-pravega. I just run it and just put this combinator retry. That just means that if this IO fails, just retry it. And that's how the optimistic writing is handled with zio. Honestly, I find this very elegant. I don't know if it's clear for everybody. Yeah. So now some little thoughts about zio and some analogy I found. I think that there is. zio, we have, of course, a process, the JVM process. We have threads and fibers, which are kind of light threads. In Pravega, there is a string, the segment, and also the transaction. I don't know how it's called, but the temporary segment before the transaction is committed. And I find there is some nice analogy between everything. And that's why I wanted to implement this connector, because I thought it would be probably easy to implement because of this analogy. I don't know if it's Pravega is is a very young but very rich ecosystem. We have many connectors from database, from HTTP, from Spark, from even to make some operator with for Kubernetes, from many. And this one has my attention because it's quite young, but it's a CQRS framework I think that Pravega could be a very good storage engine because of of course of the stream and the key value table to store the projection. Some references, and just I think I forgot to mention it's the support for transaction, because in the sink when I have the writer sample, this I have a sink, but I also have some things with transaction support. Same everything with same pattern, very. And just to show you the transaction support, it's very fun. Again, I acquire a reader, but this time the reader is this one with transaction event reader. Of course, there is also finalizer auto. Of course, there is the writer, and then there is this perfect function where I can handle the existing condition of the stream. So if the stream is a failure, I abort the transaction, and if the stream is a success, I commit the transaction. And by doing just that, I have a transaction support in the zio-pravega, which is very simple. That's it for me. I put some references on the IO, and I hope you enjoy the presentation.
Yeah, that was really informative. I wonder if there are any questions, or I might have a couple questions of my own. But
go ahead, Derek.
Well, I was wondering, the finalize auto, is that a traditional Java finalizer? Like, does it survive out of memory or process termination? Well,
no, if I keep the process, it won't be run.
Right. Well, Java finalizers, yeah, Java finalizers aren't guaranteed to run if like the JVM exits.
Yes,
like I call system.exit, maybe will these finalizers run? Are they guaranteed to run? Are they like
yes,
destructors?
Yeah. As far as I know, they are guaranteed to run if the thread is not cancelled.
Okay.
Because if the thread is cancelled, there is no finalizer. That's why you don't have to. You should never cancel a thread. Okay,
I see. So it's a part of this.
Yeah, but finalizers are not attached to threads. They are attached to fibers. Okay.
I see. Okay.
And fibers are cancelable. So as soon as the JVM is not keyed with too violently, the finalizer will run.
I see. Okay, so this is like a ZIO construct, not object finalizers. Okay.
It's applicative finalizers with much more guarantees than.
Okay. Okay, that's what I was assuming. I guess that there was something different. And then, in your kind of analogy at the end, you compare like what was it, fibers with segments. So, would there be a way to, or segments with threads inside of like the ZIO runtime? Can you increase or decrease the threading concurrency based on the segment count?
Yes.
Okay. Is that implemented, or is that
no, not yet. It will be the next
something to look at.
I have many ideas on this point, and I didn't push. But as you can see there, ZIO is very wide. Okay, also from operators for Kubernetes.
For sure. Yeah, I see.
And I really like to be able to handle this.
Right.
Okay? To detect if my application doesn't have enough core to support the parallelism, and then be able to have some operators that would be able to span more pods.
Okay.
On the client.
I see. So you could do it, I guess, you could use Kubernetes to do it across machines,
Yeah.
And you could use
Sorry.
CIO's internals to do it like within a machine. I guess.
There's many options, and as you could see, it's very it's not very hard to pay. It's very short. Everything is already implemented.
Okay. Yeah, that's really interesting. Do we have any other questions for Olivier, or? I guess we'll have to check out that event sourcing framework in ZIO. And
yeah, and I propose to the IO community if they would be interested by a storage engine backed by Pravega, and they are very interested.
Cool.
So
well,
it will be my next hobby.
Okay. Well, we'll have to follow up on that. That sounds really cool. All right. Well, thank you very much.
You're welcome. Thank you also for your support, Derek.
Sure. Yeah, that was great. All right. Well, we'll get your talk up on YouTube as soon as possible, Olivier. That was really great. I'll just, I guess, close off this meeting with a quick overview of sort of development progress in Pravega 0.10 and 0.11. So in the 0.10 release, these are sort of like some higher level features that came out. We implemented stream tags. These are like tags in many other systems, just a many-to-many relationship of labels to streams. So labels can be applied to a stream as stream metadata. You can retrieve like all the labels on a stream or all the streams in a label. Pretty typical of tags in other systems, just a metadata feature. In key value tables 2.0, sort of a refactor of key value tables, or beta version 2 of key value tables, came out in 0.10. These are built on fixed key length table segments with keys stored in the segment attribute index. That's the assorted B plus tree index. These second round of key value tables provide key ordering. In the documentation, you'll see them referred to as sorted key value tables. This enables range queries, so list all keys from A to C, and prefix queries, list all keys beginning with P. A key in the second iteration of key value tables is made up of a primary key and a secondary key. So if you looked at key value tables in the previous implementation, there was this concept of a key family. Now there's this concept of a primary key and secondary key. The hash of the primary key determines the segment or the partition that the value is destined for, and then the secondary key is optional. And then you can, given these primary keys and secondary keys, you can have multi-key atomic operations. These atomic operations are supported for all keys with the same primary key. That is, keys that are assigned to the same table segment. Additionally, in 0.10, we released a new health check service internal to Pravega. It provides a liveness endpoint. This is for the Kubernetes operator to determine if Kubernetes should restart the service. So when a service is booting, it's live, but it's not ready, for example. So the other endpoint is the readiness endpoint. This tells Kubernetes, can this serve requests yet? So, when a new pod is starting, liveness will come up, and then readiness will come up, and then Kubernetes will start using that pod to serve requests. There's a details endpoint, provides additional information relevant to assessing a component's health. The health check supports composition of health components. So, a health component can be composed of child components. And then there's flexible aggregation logic in this composition. So there are aggregation rules for coalescing a component health status from subcomponent health statuses. So that might be like all components must be healthy, or at least one component is healthy, those sort of things. There's a segment store admin gateway was added to improve the admin CLI. It allows developers and administrators to perform low-level requests on any segment. This is exposed through the admin CLI at the command line. Large events were implemented. An event over 8 megabytes is written as a transient segment that's merged with the active segment. Improvements to the Pravega CLI, where the focus was on debuggability and repair commands to maintain production clusters. So these commands included managing the key value tables, repairing the tier 1 logs, inspecting reader group contents, and managing controller metadata. Work continues there, and I'll get to that in a little bit. Transaction performance was improved in 0.11. So the transaction merge requests were sort of batched and pipelined. To previously, the call complexity was n segments times m transactions. So if I had 500 segments and 10 transactions, we'd have to make 5,000 calls. So this reduces the complexity of, I guess, batching the transaction IDs so that you just call once per segment for all the transactions you're closing or committing. And a long-term storage S3 binding came out in 0.11. So you can use AWS S3 as a tier 2 long-term storage. Work continues there on long-term storage bindings in 0.12 and 0.13. Azure Blob Storage and Google Cloud Platform Cloud Storage bindings are being worked on. I think you can see the PRs for that in the GitHub repository. More work on recovery commands, B-tree index recovery, and also recovery documentation. Additionally, bug fixes, security upgrades, and more documentation improvements will be on the way in those releases. Also, Node.js and Golang clients are underway supported by the Rust bindings. So those are, I guess, some things to look forward to, and that's what we've been doing the last 9 months or so. And then our next community meeting, a tentative date of October 13th. We'll iron out the topics, but we should be able to talk about the 0.12 release by then. We may be using release automation for that. We may demo. We have this Pravega desktop manager GUI. If people want to search that out on GitHub, it's being contributed by the King of City. He's one of our developers in Shanghai, but this is it uses the Node.js client to present kind of like a management GUI on the desktop, a multi-platform sort of application to monitor a Pravega cluster, sort of introspect the cluster, get metrics, reveal scopes and streams and all that sort of thing. So we'll do that in about a month and a half. I'll iron out the date and the exact topics, but if anyone wants to propose anything, we'll be happy to get to it. And then I guess just to close out, you can check us out on Slack. The Slack workspace is pravega-io.slack.com. You can get a Slack invite at this Heroku link. The blog, we've published a couple blog posts recently about Flink or about Debezium. The Pravega community group, that's sort of this feature. We'll be continuing with these and posting them on YouTube. We have a users mailing list at lists.cncf.io. You can search for all the Pravega mailing lists. There's a developers mailing list. And then on Twitter, just Pravega.io account on Twitter. So we'll look forward to seeing everyone at the next community meeting. And thank you again, Olivier, for your talk. That's really great work on ZIO.
Yeah, thank you very much, Olivier. It was great.
That was really cool. All right, well, thank you very much, everybody else. See you soon.
Bye. Thank you.
Bye.
See you.